Movie 2 is going to deal with the inverse cosine and inverse tangent functions. And just a quick note on notation here. You won't see it in our book very often, but we do come across in different contexts where they replace the inverse cosine notation with something called the arc cosine. And you'll see the same thing for inverse sine being arc sine, inverse tangent being arc tangent. I don't know why the different notation there. You just see that in different contexts you'll find this. One that we do in AP Calc is the AP Calc does write arc cosine instead of the inverse cosine notation. And I think a lot of it has to do with the use of -1 as an exponent. Now the inverse cosine function is similar to the sine function, except what we're dealing with is finding the x-coordinate, or given an x-coordinate, find the angle. So arc cosine deals with the x-coordinate to angle. Inverse sine goes from y-coordinate to angle. And so once again we have to restrict our domain because given some possible x-coordinate, there are an infinite number of possible angles that could get you to that x-coordinate. And so we're looking for part of this function that can go and have the domain of -1 to 1 when we reflect it. And so what we do is we limit our domain from 0 to pi. Excuse me. And when we do that and flip over the line y equals x, we get our inverse cosine function. And so that's the big change between the two functions, is instead of being limited for the first and fourth quadrants, the inverse cosine deals with the first and second quadrants. Now let's take a look at where we're evaluating a couple inverse cosines. And so once again, it's about our x-coordinates instead of y-coordinates. And so where is our x-coordinate? Square root of 3 over 2. And once again, seems like we're always coming back to this, but we are at pi over 6 for that angle. And so we would be at pi over 6 radians, which is 30 degrees. Now, the second one here, where the inverse cosine is 0, realize our cosine is 0 at two different places on the unit circle. And in fact, we always have two places where our cosine values equal a particular number. Only one of those will be in our possible range of values. And since our possible range of values for cosine comes from the first and second quadrant, the only possible answer for this would be pi over 2. Our range of values eliminates that as a possibility, and so it's pi over 2 radians or 90 degrees. Now there's two possible values from our unit circle, but if we do get something like this one where we have to take the inverse cosine of 5/7, we can use our calculator to evaluate that to be about -1.5208 radians, which is approximately negative 87.1376 degrees. Now let's go down and look at our inverse functions property. And so once again, if we're on our unit circle here, and we're at an x-coordinate, we're looking for an x-coordinate where we have square root of 3 over 2. Well, we know that we're at pi over 6 there, and so the first step would be to evaluate the cosine of pi over 6, which gets us back to what we input, the square root of 3 over 2. And once again, the reason why we could do that is because our input into that inverse functions property fit this range of values, and so input equals output. But once again, this is the one we have to watch out for. because it is a little bit different than the sine. We're going from 0 to pi with the cosine. 2 pi over 3 is within that range of values, so we know we can just come right over here and say that the inverse cosine of the cosine of 2 pi over 3 is 2 pi over 3. And if you want, you could check that intermediate step, because the cosine of 2 pi over 3 is, let's see, 2 pi over 3 puts us there, so that would be negative 1/2. And the inverse cosine of negative 1/2 is 2 pi over 3. And so input equaled output because our input was within the acceptable range of values. The inverse tangent function is a little bit different than the others, and that our domain here, instead of going from -1 to 1, includes all real numbers. And I think we'll see why it includes all real numbers when we see the graph of it. The other thing we have to look at is, why was the inverse tangent, or why was the tangent function limited to pi over 2, from negative pi over 2 to pi over 2? And so when you look at the tangent, here's our tangent function right here, y equals the tangent of x. And as you look at this, and if we look in our unit circle, we know that tangent's positive in the first and fourth quadrants here. And so first quadrant, fourth quadrant. And so if we want to, we could possibly include first and second quadrants for the domain, because in first quadrant tangent's positive, second quadrant tangent's negative. But we could also go first and fourth quadrants, because here's back-to-back quadrants with a positive tangent and a negative tangent. And so what we have to do is, to help make our decision, is just come over here and look at the tangent function. If we go and include the first quadrant from 0 to pi over 2, and the fourth quadrant from 0 to negative pi over 2, what we end up with is one continuous curve to represent our inverse tangent function. And so when we come over here and graph y equals the inverse tangent of x, what we find is, as we take our asymptotes with us, and this asymptotic behavior goes on forever as x goes to positive and negative infinity. And so that's why, as we look at this, it doesn't matter what your x values are. There's an infinite amount of values I can put into there, because I can go to positive and negative infinity. And so that's why the domain of the inverse tangent is all real numbers. So let's go and find then some of these. So where is tangent equal to 1? Well, tangent is going to equal 1 when x and y coordinates equal each other. And so that happens here when we are at pi over 4. And so the inverse tangent of 1 is pi over 4, or 45 degrees. And the inverse tangent of square root of 3 ends up being at this position of pi over 3. And I think that's one thing that we're not as good at as we are with the sine and cosine. We're very good with our values of sine and cosine, not so good with our tangent. All right, but go and check the math on that. And now the inverse tangent of negative 20, well, we have a domain of all real numbers, so it is possible to have a value at this point. And what we find, we're going to have to use our calculator, and so we would get negative 1.5208 radians, or negative 87.136 degrees. Now if we come down here and take a look at our inverse functions property, we have a change here when we're going the tangent of the inverse tangent because we can evaluate for all real numbers instead of going from -1 to 0. And when we're doing the inverse tangent of the tangent, our restricted domain is the same as the sine function, and so will be very similar to what we were getting done there. And so the tangent of the inverse tangent of -19.9, since it's all real numbers, our input is always going to equal the output in this case. And so -19.99 ends up being our answer. And here, for the inverse tangent of the tangent of 5 pi over 4, the first thing I'm going to look at is the fact that this value right here is outside that range of values. And so I need to evaluate each step of this. And so what I'm going to be doing is taking the inverse tangent of 1. 5 pi over 4 does put me in the third quadrant. Both x and y's are negative here. 5 pi over 4 has a tangent of 1, so 5 pi over 4 is going to have a tangent of 1, because that's what its reference number is. And then the inverse tangent of 1 has to put us back into this range of values here, and the only range of values from negative pi over 2 to pi over 2 would be pi over 4. Okay, the last thing we're going to look at here is kind of a combination of some of our inverse trig functions with another trig function. And we can help evaluate these by sketching a triangle. And I think the first one we look at here is the cosine of the inverse sine of 24/25. Well, realize that this expression right here finds some angle. Any inverse trig functions, they find angles. And so if we go and draw our triangle here, let's call this angle theta. We have a right triangle. And so since the inverse sine of that angle is 24/25, that tells me that the side opposite is 24 and the hypotenuse of this right triangle is 25. And if I use my Pythagorean theorem, I could show that this side is 7. And so the inverse sine function is going to help me find this angle. And then once I have that angle, I'm going to take the cosine of it. But I don't need to go and actually find the physical angle measure, because I can come to my triangle and just evaluate the cosine of theta using SOHCAHTOA. And so the cosine of theta is 27/25. And so the cosine of the inverse sine of 24/25 is 7/25. Now let's come down to example 2 and kind of do the same thing. So here we have our right triangle. So we'll set this up as angle theta, because there's our inverse tangent function, which is going to give us theta. Alright, so tangent is opposite over adjacent. And so 5 is a ratio of 5 to 1, which would make our hypotenuse the square root of 26 by the Pythagorean theorem. And so now we're going to look at what is the secant of theta in this triangle. Now that we have the triangle set up, we can replace this inverse tangent of 5 with theta. And remember, secant is the inverse of cosine. So 1 over cosine of theta is 1 over the square root of 26, which is the square root of 26. And so this expression, the secant of the inverse tangent of 5, ends up being the square root of 26.